Hey everyone! So if you've been getting the hang of Thevenin's theorem, you've already got one of the most powerful tools in circuit analysis down. But what if I told you it has a partner? Today we're diving into the other side of the coin, Norton's theorem. Seriously, think of it less as a new topic and more as Thevenin's natural-born partner.
Okay, so you know how to take a big, messy circuit and crush it down into one simple voltage source and a resistor, right? But what if it would be, way easier to think about that circuit in terms of a current source instead? Well, that's exactly the question Norton's theorem is here to answer.
So on the left, you see our old friend, the Thevenin equivalent, a voltage source with a resistor in series. Simple enough. But check this out. On the right is the Norton equivalent. It's the exact same circuit, just represented with a current source and a resistor in parallel. This idea that you can have two equally valuable ways of looking at the same thing is called duality. It's a huge concept in electronics.
So let's talk about this concept of duality. What does that really mean for us? Well, it's pretty simple. It just means that for any linear circuit, we can simplify it in two completely interchangeable ways. We're just swapping our perspective, from thinking about voltage sources to thinking about current sources. And this slide just nails the difference, doesn't it? Thevenin gives you that voltage source in series with a resistor. Norton, on the other hand, hands you a current source in parallel with a resistor. And here's the key. One is not better than the other. As far as any load you connect is concerned, they are identical. They're just different tools for different situations.
All right, so what actually makes up a Norton equivalent circuit? Let's get into it and break down its core components.
Okay, so here's the official textbook definition of Norton's theorem. It says any linear network, I don't care how complicated it is, can be swapped out for just two things: a single current source, which we call I sub n, sitting in parallel with a single resistor, R sub n. That's it.
And this is what it looks like. It's beautifully simple. You've got your current source, IN, pushing out a steady current, and right next to it, in parallel, is the Norton resistance, Rn. Anything you connect to those terminals A and B will behave exactly like it was connected to the original, much more complex circuit. It won't know the difference.
So theory is great, but how do we find the actual values for IN and RN? This is where the fun begins. We're going to walk through an example using what I like to call the short circuit mindset.
Let's work with this circuit right here. Our mission, should we choose to accept it, is to replace everything inside that shaded blue box with a simple Norton equivalent. And the very first step, just like with Thevenin's, is to say goodbye to that load resistor, R sub L, for a minute. We got to get it out of the way to see our terminals.
Now to find the Norton resistance, Rn, we're going to follow a procedure that, well, it should look really familiar. After you pull the load, you kill all the independent sources. Remember, voltage sources become short circuits, just a wire, and current sources become open circuits, a broken wire. Then you just look back into the terminals and calculate the resistance you see. And see what happens? We've shorted out that 9-volt source. Now if you look back in from terminals A and B, what do you see? You see the 3 ohm and 6 ohm resistors sitting in parallel with each other. Now if this whole process feels like déjà vu, that's because it is. This is the exact same way we find the Thevenin resistance, Rth. And that brings us to the most crucial point of all. Rn is Rthin. They are identical, one and the same. You already know how to do this part. So for our example, a 3 ohm in parallel with a 6 ohm gives us an Rn of 2 ohms. Easy. Okay, now for the new part, finding the Norton current, IN. For this, we bring all our sources back to life. But here's the twist. Instead of leaving the terminals open like we do for Thevenin voltage, we connect them together with a short circuit. The Norton current, IN, is literally the current that flows through that short. And watch what happens when we short terminals A and B. It's kind of cool. The 6 ohm resistor is totally bypassed. Current is lazy, right? It's always going to take the path of least resistance. And you can't get less resistance than a short circuit. So all the current just zips through the 3 ohm resistor and right through our short. Using a little Ohm's law, 9 volts divided by 3 ohms gives us a short circuit current, or IN, of 3 amps. Boom.
Okay, so we have both our pieces. Rn is 2 ohms and IN is 3 amps. But how do these numbers actually relate back to the Thevenin circuit we know and love? Well, this is the big aha moment. This is where we build the bridge connecting these two worlds.
And one of our sources just says it perfectly. You can get from Thevenin to Norton, or from Norton to Thevenin, just by doing something called source conversion. Basically, you can think of them as two different languages that are describing the exact same thing.
And this is the magic formula that lets us translate between them. It's the bridge. And look, It's just Ohm's law. The Thevenin voltage is just the Norton current multiplied by that equivalent resistance. So for our example, 3 amps times 2 ohms, that gives us a VThev of 6 volts. It is really that simple to hop from one to the other.
And there you have it. This is the power of source transformation in action. On the left, we've got our Norton equivalent we just calculated, and on the right, it's Thevenin twin, which we got directly from our little bridge formula. You can just toggle between these models depending on what kind of problem you're trying to solve.
So let's just do a super quick summary of the whole procedure. Step 1, find Rn, which is exactly the same as Rth. Step 2, put all the sources back, and then short the output terminals. Step 3, calculate the current flowing through that short, that's your In. And finally, step 4, just draw your new circuit with In in parallel with Rn. Done.
So you might be thinking, okay, that's cool, but why? Why do I need another theorem if it's just equivalent to the one I already know? It's a great question. Why have 2 tools in the toolbox? Well, because sometimes you need a screwdriver and sometimes you need a hammer. Let's see when Norton really shines.
Norton is your absolute best friend when your circuit is full of things in parallel, or when it has a bunch of current sources. Think about it. The Norton circuit itself is parallel, so adding more parallel loads is super easy. And if you're trying to find the current in a branch, well, thinking in terms of current sources and current division often makes the math way, way simpler.
And that really brings us to our last big idea for today. We've seen how voltage and current, series and parallel, Thevenin and Norton, they're all duals. They're just 2 different ways of looking at the same thing. So that leads to a pretty interesting question, doesn't it? What other dual concepts are out there? Not just in circuits, but in other fields of engineering or science. Where else can you find 2 different but equally correct ways to describe the same system? Something to think about.